control of autonomous agricultural robot trajectories using an edge fog architecture. He is from a French institution in France. I can't, decipher this, but you can. All right. Sandro, thank you. The floor is yours.
Morning to all of us. Sorry for my English with the French accent. So, okay, that's life. So only to say that this work has been funded by a European project that is started. It's going on and some French project. Okay, this is the plan, the context, motivation, the proposal, some experiment, and then the work and the conclusion. So the context, so the institute where I work is the National Agricultural and Environmental Research Institute of France. Okay, so in this moment, what we are working on is we work on the usage of robots that are some small autonomous tractor like small Tesla, and to do what? To do, we hope, some agroecology practice to reduce input and so on. And if you want to do that, today the French law, but also the European law, oblige you to be 5 meters far from the robot. You must follow the robot.
Okay.
It's quite Europe stuff. So the idea is to have a system that you can see the robot from distance, and maybe we are able to do it to guide it with the PlayStation stuff. So this robot generates a lot of data that is in real time, and this data usually is handled by what we call data stream management system. What these kind of in-memory database are able to compute query like this, calculate the minimum of speed of each robot every 5 seconds. So the frequency the query is executed each 5 seconds. And then they can use a window to say, collect me data in a window that is we say here, 20 seconds. So data streams, management streams are very, very, there are a lot of things like Oracle, Microsoft that use this kind of systems. So the problem is that when you are in the field, you have not network, because the 5G is what they say, but in real life, farmers have not it. Then you have too much data that arrive. And what is important is that you cannot let the robot move for 1-2 seconds without a control, because you can kill someone or you can kill the robot. So we need a system that is able to query, to understand where the robot is in real time. So for that reason, we think that we can use this kind of data stream management system. But they come with a set of predefined query operators, and we cannot modify them. Oh, you can, but you have to code thousands of code. So here I don't. You can see here some real query that we use in our case study that is about the robot malfunction and risk. This is a real robot that we use. Every 5 seconds, give me the speed, because if the speed is 0, it's too high, you have to stop the robot. Or you can also monitor the work of the robot on the field. Give me each 1 minute, 2 minutes, 5 minutes, what is the delay of the robot task, because it is like today, maybe we are too long. It's like that. Before to go on, the idea is, we try to classify this kind of query because why? Because the idea is to see how to implement it. So we can say that we have two kinds of queries: the mono-trajectory queries that use only one trajectory. We are interested to only one robot. The robot is good. The engine of the robot is good or not. And the multiple query where we need to use multiple robots, for example, our robot colliding. Then another important point is that we pick it from the database theory that you have two kinds of aggregation query. Distributive aggregation are aggregation that can be computed using sub-aggregation. For example, the max of the half and the max of the half, and then I put together to have the max. Then you have non-distributive query that are the most hard because you cannot pre-compute. So you have to pick all the data like distinct count. So to do that, the idea is to how we implement this kind of stuff in our system. The first step that we define what is robot trajectory, so it's quite simple. It is a x, y coordinate, a set of numerical data that can be odometry, the speed, the time, the steering angle, and the time sum. Here you have two robots like that. And then what is a continuous query? The idea is to try to see all the part of a continuous query and then try to how to implement it. So you have a data source. The data source can be a stream, is a data that is never stored, like the robot data, but you also can have some relational data, for example, the geometry of the plot where the robot is in. You have then some selection, what the data that you want to retrieve, and on that kind of data you have three different kinds of predicate of selection: alphanumeric, the name is Alpo, spatial, I am inside this polygon, and the spatial temporal, we are at the same time at the same place. Once said that, and then you have the aggregation, and you can use numerical aggregation like min, max, and other stuff, or spatial temporal one. The window, that is how many data I have to aggregate. If I am here, each 5 seconds, I am here. The window is how many seconds last I take. And finally, what is new for a continuous query is that the frequency is the time when the query is triggered. In that kind of system, like when you are in your GPS with Google, you can see that when you arrive to the Carrefour in Croce, your Google send you more data. And when your robot is in a critical situation, your query must be triggered with high frequency and maybe with a small window. So now we have a real farm, we have some real farm, and we have some real robot, and we have some real guy that must use it. And so the idea is how to implement it. We have the robot, and we have usually we have a cloud, but I say you that there is no 5G, so the robot cannot send data to the cloud and back to the farmer. Also because it's too long. So we decide to use an edge fog architecture. The edge is the robot, the fog is a small PC like that. And why? Because it allows you to reduce communication time. So what we have done, is in a previous paper we defined this architecture. So there are a lot of layers component. I don't provide details about this one. What I provide you details is of the data producer. So we have robot, but also sensor, humidity, soil, and so on, blah, blah, blah. And all the data are sent to a message broker like Kafka. I don't know if you know. Kafka is used by Twitter and so on to ingest all your useful tweet. And then data arrive to the farm where we have this. So let me go into details. I have 5 minutes, so but okay. The first stuff is what data stream system I can put on the robot. You have there are a lot of stuff because it should be lightweight, because you cannot go to inside each robot and change and maintain the software on your robot thing. So we use Esper because it is only an API, but Java API, but it does support spatial data. So to do that, what we have done is that we don't want write code. So what we do that we use an in-memory spatial database. It's a database that don't store data into the disk, but store data in memory, so it is fast. And so with the coupling the two one, we arrive to have a query, continuous query that use spatial data and spatial temporal data. Okay, for the server, for the farm server part, we use GeoFlink. There are a lot of open source distributed to scale up this kind of continuous query. But the only one that we think that is now the good one is GeoFlink. It is an Apache software. So now back up to the kind of query. So that is that all the query. So that is when we have a query where we have to implement it. When you have a mono trajectory query, the only thing that you can do, you must implement it inside the robot, because so like that the robot is moving on. It compares his real trajectory to the predefined one with the timestamp. So in that way we can compute the delay. Then at the fog level, in the farm level, we can compute the multi-trajectory query that are non-distributive. In that kind, it is the collision. We send all the data to the server of the farm, and we calculated the distance between that points. And then we understood that we can split some of this query, compute partially on the robot and partially on the farm level. For example, each second compute the max speed of all robots in the last 5 seconds. So each robot compute is max, send the max to the fog, and the fog recompute the max. Some experiments we have here at age level with our new extension of Esper. We test the average speed and IM inside the polygon. We can see that performance are some milliseconds, so with the high frequency. So we can say that the robot is able to compute it. At the fog age, so what we have done is that some query like collision that are not distributed, but we can also try to change a little bit in order that they become distributed. For example, for collision, what we have done, so the robot must follow a predefined trajectory. Okay, so what we have done using is speed. We define a buffer for each trajectory, and then what we do is that at the edge in the robot we see if I'm not outside of the buffer. If I am inside, everything is good, and I don't send data to the file. But if only when I am outside the buffer, I send the data to the server in order to try to understand if a collision will be. We can see that we compare the performance with our HFOG against the performance to the server side. You can see that there is a big and important stuff. So I want to finish to say that robots are very sophisticated stuff, but they are not able to do something like that. It's quite strange because robot guy, men always men, but robot people. The idea is the most autonomous I am, the better it is. So their work is very close to other kind of technology. Thanks a lot.
Thank you, Sandro. Very interesting presentation. Are there any questions from you, the audience? So
why we use the robot?
No, not that one. But you talked about these experimental stages that you presented, and you have a farm, and this is what you said. When do you think this could be employed, such a system in real life? So to roll it out.
So
any plans?
Yeah. The robots are now used. We use the robot, real robot.
Yeah.
And they are really used. And our system is what is the problem is that the robot firm they have their own supervision system.
Okay.
But this supervision system it's quite simple.
Mm-hmm.
So what we are doing now is that we use it at farm now in our farm. At the moment it is closed. It's not open to, but we are working to, because there are some. We hope to put all as open source at the end of the project, because we are finishing the cloud.
Okay.
Where cloud layer where all the data is stored. So they want to store files.
And once this has all been done, you were at the beginning of your talk. You were talking about agroecological applications. So, so what do we have to think about when it comes to agroecological applications? What are these robots?
What robots do?
Supposed to do?
Okay, for example, you know that you can eliminate weeding. Weeds.
Okay.
Weeds, you know weeds.
Yes.
Weeds. You usually use Roundup or other.
Okay.
You can use a mechanical to remove.
All right.
There are some solutions, but these solutions are usually put on large tractor. And these large tractor, what they do first, they compact soil.
Because of that tires.
And because weeding is you must go a lot of time into the field to remove the weeds, bad weeds. So you cannot do with a big tractor because you compact soil, and you have a human that have worked too much long. So the idea is to do this stuff. Another stuff is what we call the pixel cropping. Pixel cropping is your crop is not in lines like that. Your crop is like a square.
Curved lines.
And what you do is that you with robot you can have a really precise movement, and so your robot will work a lot of time on the field, maybe all the night You can
Yeah.
spend all the night work. Of course, we like it.
Yes, sure.
And this stuff, and there are a lot of stuff, agronomy stuff, but I want to,
Okay.
because I never told.
You mentioned about the speed control and getting
For
the speed
example.
information. Do you have some sensors in your robots
Ah,
to
yeah.
get it, or you calculate from the
No.
location?
No, the robot have a lot of sensor. It's like your Ferrari. You have a lot of odometry data, and you have the speed. You have the steering angle. You have the wheel working. If your wheel is working well or it is a vuoto, andare a vuoto.
Is revolving too fast. So.
Yeah, without moving.
Yeah.
Not without read on the sun.
Yeah, exactly. It's stuck.
You do, but you don't go on. You have a camera, you have a camera. And also, now we start to handle drones, but it's start to be some new data.
Okay, please.
This is just a curiosity. I mean. In recent times, there is this huge amount of project in the countryside devoted to abandon land to be developed with agri-photovoltaic. It means basically stripes of photovoltaic cells, and inside land, usable land.
Yeah.
It means very, very long and very oriented lanes, let's say. I would probably this would be one of the best things for a robot who is just going ahead without any particular difficulties. Instead, for a farmer, this is basically difficult because it needs to stay online and without damaging the equipment. I was asking, I am asking, if do you think that this new kind of energy development that is supposed to help the abandoned land to be redeveloped in some very hybrid way. Do you think that robots could be take advantage from energy developed by the photovoltaic cells so as to be more powerful and then be able to
all robots now are electrical engine, okay?
Yes.
So the idea they have not to. And what my colleagues try to do is that that robot, as I say, robot work too much long, and so the battery is like that.
Yeah.
It's not a Tesla battery. Okay? It's like that. And the idea is to put in the field the recharge.
Yeah. Okay.
So having the energy point into the field where I can recharge my robot will be this is a real problem for the robot, the recharge.
Sure.
So the time you go back because field, it's very big, at least in France we have big out there. So if you have time to recharge and continue to work, it could be. So,
Okay, please. All right. Okay, we're done. Okay, if there's no more questions, then thank you, Sandro, for this presentation. Thank you for keeping to the time. We're well in time. Okay, I suggest to skip the second presentation because none of the Lamborghinis is here, and we move on to the third presentation on our timetable. And I would call Domenico Carmada to the floor. He is presenting on harnessing AI for future scenarios, exploration approaches for sustainable planning in Taranto, in Italy. Domenico, please.
Thank you. This paper, the paper belonging to this presentation, making this presentation, a very curious acceptance path. I mean, it was firstly rejected because the algorithm seemed to recognize a very completely made by generative AI. Because of course, this with AI, we to deal a lot with Springer to let the paper be published. But anyways, okay, this is a note, a very preliminary note. It's a some synthesis of a kind of a project that we are carrying about and we're taking Urbari, connecting with the redevelopment. I come from a planning sector, spatial planning sector. The development of areas in industrial crisis. Taranto is one of them. And at the crossroads with the study on modeling approaches to support decision making in let this development project be actually activated. Taranto is here, south of Puglia. Actually, the industrial area is basically as large as the urban area. Very big. It's built in the 60s, but it grew in time 4 times compared to the 60s. Although there are many problems during these decades, the area continues to grow until the late 70s, and to produce pollution. Of course, pollution was not even a problem when the industry was set up. Yes, it was at the time the chronicles of the time healed the new industries because it took some new work, new job to people, and this caused an increase in many, particularly in respiratory disease. Okay, just to remember some. The employment now has decreased very much. So since also the area of people coming to work has decreased very much, but the envisioning of new jobs boosted a very expansive plan in the past. So housing is still now going to increase. So causing, for example, the abandonment of the city center and the problems to maintain the city center. But, well, actually, the service system, the infrastructure is also not adequate to this increase. So in the last part, in the peripheric part of parts of the town, there is not infrastructuring a very adequate infrastructure, and so people basically depends on private car, increasing pollution problem. I'm sorry for my presentation. I am still trying to recover from yesterday night, but anyway.
All right.
Okay. Well, the last day it's always very difficult for presentation.
Yeah,
Okay.
yes, you do.
Okay.
But you make it.
Thank you. I hope for your compassion.
Yes.
Master plan is very difficult in a city like Taranto, basing on these problems, on these issues. It's very difficult. So, in order to understand what kind of alternative development could be assured to this kind of critical city, we were in the group of the master plan making in last years, and we decided to apply some methods actually aimed at envisioning new alternatives for the future, starting from collecting knowledge from people. And our long run intention was to build an architecture that could be useful for dynamically use this knowledge raised by interacting with people to support decisions by the administration. This was the aim of the final aim. And this is a very, very common method, schema of the method that was based on idea born in the 60s, actually, and then after some decades, more oriented to make some steps. So this is a steps that by which the knowledge is structured, coming when meeting, when collecting it with local knowledge agents, local people. This is some example, actually, just an old example. By the way, this was just Turkey, carried out in the past in Kuşadası, which is close to Izmir University. The traditional approach is very easily made with papers on the walls. Then we use computers, and with PC-based, an evolution of this PC-based approach was used to build scenarios in Taranto. This is the perimeter of the town. These are districts of Taranto. And for each district, we actually try to collect people to build this knowledge. This was a problem sometimes because, as you see, for example, Tamburi district is a district which is close to the closest to the industry, and people did not trust that the plan would drive to anything good, so it didn't come at all. It is a problem how to make people encourage people to come, because probably their knowledge is one of the most important to build the future, and it is a problem. Conceptual maps during these meetings, and this is a synthesis of the visions carried out with this hybrid method of PC-based interacting with people. The visions for the future for the people, by the people. They actually are called to group. I'm going to synthesize a very long actually procedure. It took something like 1 week. So these are a couple of slides. They are not completely representative of the process, but anyway, the group's visions made by people themselves, 5 of them. So in the end, we thought that using an LLM and a large language model approach, we could try to take advantage from this kind of schematic approach. And let's say what happens, asking to, in the first step, let's say, of our long-term research, ask to the AI respondent, let's say, same questions, suggestions we call it. We've made the same precisely the same questions made to people, and what do you think about what is Taranto according to the images that characterize Taranto in 50 years? This is what this is actually we used OpenAI, ChatGPT, Copilot actually at that time because it was free. It was one of the first free. There are a number of them. So I think there are 5, but anyway. So an example of what you say. This is of the AI said. This is a particular. It is very detailed in some way. There are some issues in a way that we will deal in a while about. Can you aggregate them? Yes, let's aggregate into visions. These are the visions. We just made the same thing that we basically the same thing that the same process that we made usually by building scenario with people. Scenario, not AI-based scenario building, the traditional scenario building versus AI scenario building. The red ones are fields that are not overlapped. Yeah. The other are overlapped. So it is, for example, it's very curious that people apparently didn't say anything about healthy and active city as a whole. They didn't see it as an image, but instead the AI scenario building pointed out that. Okay, the iconic Taranto. It's something that belongs to a vision carried out by. This is what we saw in the after discussing about it, applying some of visions that are usually designed everywhere. Which image do you prefer? And this is why green and sustainable towns among the ones that because we need to understand how to implement this kind of vision because the process asks people to it's a very long process asks people to implement. This is the continuation after identifying vision. People are asked to say what do they think, how do they think they can get this vision implemented, what are the obstacles toward their implementation, against their implementation, and what are the funds, the resources that are, need to be used. This is what, okay. In the conclusions, they are very, let's say, they are very not definitive conclusions. Just a way, the path is very long. It is undoubted that there is an advantage in terms of speed. I mean, it took a couple of hours, 10 hours in the worst, at worst, to generate scenarios. This is a problem. The time, you just imagine, after this on-field 1 week period of interaction, the administration, local administration, having not taken any kind of implementation activity, they just decided to give up. No, it took too much time. Sorry, we cannot go because it took so much time actually. So time is a problem, is an issue in terms of policies, in terms of politics as well. And so having something that is able to suggest something, some scenarios in a bunch of days, hours in this case, is something that is longed by administrators, by policymakers. Of course, they cannot catch the subtleties because all the nuances of the divisions, the feelings of people cannot be taken by, let's say, a machine-based approach. Scenarios can be very general and not very realistic. Sometimes they tend to imagine a context that realistically people cannot implement. And they are generally choose. For example, we made another experience in another town, and in that town, the plan had been already almost finished. Documents had been stored on the internet, and then the machine, the AI machine, just took the issues coming from those documents to provide visions. So it just copied what it found on the internet. The thing of the issue of knowledge, AI just manages existing knowledge. Is, let's say, statistical approach. So it just takes documents and carry out some synthesis. Instead, when you collect people by dealing with these issues, they just generate new knowledge. It is creativity is one of the cue to find out, particularly in critical areas, what kind of alternative future can be pursued. And this is something that it is difficult for an LLM model, a generative model, to draw out. Of course, we cannot deny the fact that the AI approach can represent a good way to envision possible suggestions, ways to proceed, to explore, and then trying to select for the policymakers. Policymakers are the ones who decide in the end. You can do whatever plan you like, but in the end, policymakers decide. They can also decide to take the plan, make a ball, and put it in the trash. So they decide. This kind of approach could allow measures, for example, the administration, to explore some directions, then try to collect more knowledge and decide what kind of actions can be carried out. So there are some possibilities to enrich this kind of knowledge, probably using a sensor-based approach that easily can be integrated into this architecture. For example, looking at physical issues that can be easily managed and then open up more alternatives. The cognitive exchange raises some other possibility. I think it's the last slide, this one. Because knowledge, the more complex the knowledge, the more faithful the plan. But the complexity means the difficulty to manage. So it's an oxymoron somehow, a paradoxical approach. But we think that looking at some experience using formal ontologies that try to give a structure to complex knowledge, by taking this kind of approach into an architecture like that, this could also save somehow the complexity of the whole. there are some experience made just a couple of years ago. This is onto GTP, for example, where generative architecture they are not conceptual based. So ontologies are conceptual based. So there is something to be. It is difficult to merge the two things, but there are some approaches in this. This is what you see. This is the scenarios that we are trying to implement for our research in the future.
Thank you, Domenico, for your presentation. Any questions?
I have a question.
Okay, right.
Thank you for your presentation. I really appreciate that your approach is a bottom-up approach, especially in Taranto. That is a lot of problem of environmental problem, but also a social problem in the city. And do you think that you say that in some neighborhood, for example, in Tamburi, just 5 people coming, as no one is citizen, as I know. Do you think that in this neighborhood, maybe because they didn't trust the process, so they didn't come? Maybe because in this way you have a list of ideas that you want to implement in some strategic plan. You understand? Do you think that display this idea on a map, just draw it, can be more easily to understand, also for people that are not expert in the field? And in this way, you can also using not like a large language machine, not working on text, but working on map. So some sort of a generative approach, but especially constrained generative approach can be useful also for the policymaker to visualize where the people want a park, because sometimes there is I want a park, I want a font, I want a new plot, but where to where to draw it on a plan, it's a dark task. So sometimes the policymakers say I don't want it, but if people say we want here this one, they can negotiate in some way. So do you think that this strategic plan or display during the process where to change something in the neighborhood can be helpful? Or
Yes. I said at the beginning. I said that there are basically 2 branches of researchers. The branch of research looking at the substantial knowledge, because this looks at the model, the merging with substantial knowledge with a modeling approach. But that brand of this, yes, they use. We have used maps. We have used some tools that allow to write maps also remotely. We've done it a lot. The problem is now that LLM models are not still able to manage the dynamism of the issues behind maps, because you can make snapshots, but people can change it. So how to include this into the architecture? This is a problem, because we are looking at how to make an architecture to be used for policy making. This is another issue. That is a very good question. It is another issue that we are going in the future to try to include in this architecture.
Okay, thank you. Other questions, please.
I wonder if you have already asked recurrently the same question to the GenAI. I will try to ask again and again the same question, because I guess it returns the different response.
Yeah.
So, and also the other question, maybe discussion. We have different backgrounds, different cultures, different personalities, so we may claim different options in the city. Yeah, so even in Taranto, maybe there are other cultures living there. Maybe if you collect people in there and they can negotiate and discuss, as you say. But when I maybe cannot do that. Yeah.
Yes.
So maybe you can create some agents by prompting the generative AI and try to make these agents discuss.
Yeah.
Okay, if you give it title, maybe they can discuss that and give the results to comment on your plan.
Yes, also these are very good questions, very contextual actually. The first question, there is the prompt is so important, prompting is so important in this field that there is a branch of study called prompting engineer actually, which is something very paradoxical in my way. You make the question, you don't like the question, so you make the question again, you still don't like, you find out how to. I cannot deny that.
Not more I did.
Yeah, I don't. Yeah.
Even
I
for
cannot
the same
deny that.
question. Even for the same question, it turns
Well,
different
no,
answers.
what you're asking is that is right, because asking the same questions you can have different replies, different responses. This is strange, but because the LL models doesn't reason, they just make a comparison on documents and just a second.
On the same stuff.
Okay, but I come back to you
If I can. I think that when you prompt engineering everything that do you want, you must be sure that the AI knows what you are asking for. It could be when we make some prompt engineering for generation of code, we must be sure that he know SQL, or in that case, you must maybe to the prompt engineering stuff, you should maybe try to understand if you know what are the social and economical main feature of target before to give him the question.
Yeah.
The more it knows the question, the more the answer will be the same. Only to okay.
That's not a question. That's a statement. You are right.
We suggest, because when you prompt engineering, the first question is, do you know what we are talking about? And the expert must say, okay, it knows, or it. Otherwise, the answer could be.
But my experience. My experience, but my very recent experience. I'm not of the field, of course. I used to apply. My experience is that machine never knows. Whatever you do, they never know, because even if you try to raise its contextual knowledge, it can just take another way and come with other questions, other responses coming from other branches of documents that are in its storage. That is my experience that it is always a problem till now, up to now. The second one we have tried to do. There's several experiments. We have tried to do an experiment for the city of Bari in this case, assigning a different stakeholder positions to the machine. You imagine that you are a farmer. What are the vision? Imagine that you are an old man, retired, or you are a tourist, something like that, entrepreneur. We did this. Well, in the end, some very interesting issues came out. But when you do that in the traditional context, you are pretty sure that the people will reason, particularly with her or his experience. So you are asking to a farmer because he is a farmer. It's not simulated. He is a farmer. So you know that if he say to you, look, photovoltaic is damaging my country, it is not a machine that is it's a real problem. So you need to take it into consideration.
Okay. Any more questions? I would like to ask you, you were presenting these scenarios developed with AI. Now, have you tried to, let's say, visualize one of these scenarios for the people involved, for instance, a 3D model, so that they can look at it and get on further discussing things and
By
using
using the AI.
Using the AI results, and then having it presented, having it discussed with the people, and then maybe changing what the AI and further developing. You mentioned it on a, let's say, textual or oral basis. I'm talking about the visual basis. Maps. 3D is easier to understand than 2D when it comes to redevelopment, for instance.
A colleague of mine is dealing particularly with what is the impact of visioning, visions elaborated by the AI, and shown to people. But the problem is that in this case, a typical bias comes out.
Yes, sure.
Because you are telling people this is a vision. What AI draws out from your words, but probably it is not what they are thinking. They are.
But you confront them, so then they can react.
If this is one, but no, it can channel. The risk is to channel the comments. That is the problem. Instead, the other question that you raised, which is the gesture. Yes, in the past we used sensors to enrich knowledge remotely. Because look, I am making gesture. This seems something. So other eyes, and this is something that enriches knowledge. But still, we are very embryonic moments to make the whole thing work together.
Okay, thank you. Any more questions? So then, thank you, Domenico, for the presentation. Thank you. Last night did not have a trace on your presentation. All right. Now we come to the next presentation. There are two of the authors present. So the presentation is classifying human activities in urban spaces with a multimodal AI towards a massive assessment of urban affordances. And it is authored by the people that you can read here. If I pronounce any of those names incorrectly, please excuse me. Ivan Blecic, Alessandro Flores, Giulia Gilberto, she will start presenting, and Andrea Truffio of the University of Cagliari, and he's of Sassari. Okay, Giulia, the floor is yours.
Thank you, Professor Arsch. I'm Giulia Gilberto, and I'm a PhD student at the University of Cagliari, supervised by Professor Ivan Blecic, who is here and who is a co-author. Our research project has this title, Classifying Human Activities in Urban Spaces with a Multimodal AI towards a Massive Assessment of Urban Affordances. So we focus on a specific category of urban spaces that are public spaces because they play an important, crucial role in shaping human experiences, social interactions, and people capabilities. We will go deeper in this concept later. So to study public spaces, and in particular public open spaces, urban spaces, we have to assume a position and a perspective that was introduced since 1960s by some pioneers such as Jane Jacobs and Yang L, who highlighted the importance of creating spaces for people and assuming a human-centered approach and perspective, rather than rely on aesthetic forms or just on technical solution for built environment. So what we have to do is to look closely at real cities between buildings, because there are the most important things in cities. So to following these ideas, there has been a growing demands for methods that for studying the complex relationship between people and urban spaces, and to better understand how people use the space, how urban spaces are used, and to inform public policy and in general to guide the transformations of cities. To understand how urban spaces are used means to understand how people act in the space, how people perform different behaviors in different spaces, and we know that people are engaged in activities that are characterized by interaction with objects, with other people, and also with environment. And they act with an intention to achieve some goals and certain functionings. When we talk about functionings, I have to clarify the terms, and we have to refer to our main theoretical framework, that is capability approach, in which we can define capability as the ability of individuals to achieve desired states, functionings of well-being, to become something, and to have something. Considering opportunities linked to the availability and affordability of resources as key elements of the quality of urban life. So, as I said before, functionings are the potential states whose alternative combinations reflect the capabilities. They are the desired states that people can choose. So we can consider capability as a set of functionings, and in our case, our functionings refers to doing what people think of value. But when we talk about capability, we refer to a combined capability. There are two types of capability, or it's a dual dimension, because there is an internal capability and an external capability. The internal is the ability of people, and the external one is referred to the opportunity given by the urban space, by the environment. So the opportunities that are relevant to the achievement of specific urban capabilities can be considered as a broad set of conditions related to the urban space, and within this we can recognize the affordances in the sense of Gibson has a subset of these opportunities which are linked directly linked to the physical characteristic of a space. Just to make an example and to clarify what is an affordance, we have, for example, an horizontal and not vertical surface, a flat and not convex surface, and sufficiently sized related to an individual, a person. And so we have a surface that provides support, and people can walk, can stand on this surface, run, and so on. But they cannot, for example, swim on this surface. So our objective, this study aims to develop a multimodal AI tool for automatic observation of activities in urban spaces in order to assess people activities linked and related to the affordances of spaces. This is just a first step towards a bigger goal, that is a massive assessment of affordances of urban spaces. That is more complicated. So our tool has to analyze some photos of open public spaces and classify people's activities following a specific protocol that we have defined. And this process can highlight the presence of different social groups and their behavior. And this pattern can be related to the affordances relating to the public space. So we have defined the classification protocol that I mentioned before, that consists in 5 features that are connected with the concept of affordances. So we classified people by age, gender with an error, body posture, activity level, and social configuration. Body posture, if people are standing or walking, for example, seated, recumbent. Activity level, it refers to the movement and dynamic activities. So if people rest and are sitting on a bench, for example, they are engaged in a sedentary activity. Moderate if they are walking, or vigorous if they are playing some sport or I don't know. Social configuration is referring to the social configuration. So if people are in a group or in a couple or alone. After several experimentation with many multimodal strategies, we identified the most how I can say the most efficient. Thank you. The most efficient sequence pipeline, starting from a photo of a public space with people, and we have implemented a faster RCNN algorithm to person detection, and then people and person and individuals are grouped in bounding boxes that are clustered when they show like an intersection or they are very close. So they are grouped in a cluster, and then clusters are cropped, and cropped regions are expanded and give to a multimodal large language model. So to implementation of GPT conduced to through image description that has a narrative description of the images, and then we can start the information related to the 5 features that we identified before. So we have tested the tool to validate it. And for data collection, we have photos of open public spaces. In particular, in this case, we have 24 scenes across 5 open urban public spaces in Cagliari, Sardinia, Italy. And so, for the analysis, we have conducted the analysis in 2 ways: a manual evaluation, in, let's say, in an analogical way, and an automatic evaluation with the pipeline that I described before. So we have classified people's activity following the protocol, and then the 2 evaluations output were compared. So ground truth results from manual evaluation and estimates results from automatic evaluation. This is an example of manual evaluation. This is a photo that we analyzed, and we have 7 social configurations in these pictures. And for example, configuration B, we have a man, an adult. He is walking, so the activity level is moderate, and he's working, so it's upright, and he is alone, so it's a solitary activity. I don't know what is it, but I can
guess it's from the.
It's some image that is not.
Okay.
No.
Okay.
Maybe it's
Okay. So I will show you the results of comparison. In this case, we have people count per image, and on the left side we can see the scatter plot and the distribution of results, which and the pattern is following the line, so it's a good result. And for total count of people, we have 462 for ground truth, so from the manual evaluation, and the algorithm output says that we have 438 people. I will show you some scatter plot for each feature that we analyzed. So we can see for sex, the distribution of results are correlated. So the points are a couple of values, one for ground truth and one for estimate results. So if they are following the line, it's there is a correlation. So this is a good results for sex for this feature. For body posture, the same. So we can see the pattern. Activity level is not so good. We can see points far from the line, and also for social configuration. To assess the alignment and the distributional similarity, we calculated the per category error metrics and global divergence measures, comparing ground truth and estimated category distribution. So we have, as global divergence measures, we have chi-square distance, Kullback-Leibler divergence, and Jensen-Shannon divergence that I highlighted. And we noticed that for sex and body posture, that showed a good pattern following the line. We have the lowest value for this for the divergence for the distance, so it's a good result. And while for activity level and social configuration is a little bit higher, the lower value indicate a consistency between the results. So in conclusion, we can say that the algorithm performs very well for sex and posture, but we have some limits. We notice some limits for the activity level and social configuration, and in our opinion, it's linked to it's because of the nature of the input data, because we have a static photos. So, for example, activity level that indicate how the movement of people. It's difficult to recognize, and for social configuration, there are some programs. For example, if you can see just the head and feet of people, but not the entire body, the algorithm recognizes more than one individual. So the next step to improve the classification is to submit a video clip or a sequence of frames to resolve this problem and this overpass these limits. Okay, thank you for that.
Thank you very much, Julia. We have an unexpected virtual presentation. This is the last one. The two Rodrigos and Camilo, and they will be online in a very short time, so we don't have too much time to finish the session. Are there any questions?
Just one question.
Yes, please.
What kind of the algorithm did you use to capture the images?
To capture the images, we just took photos with the camera.
As a regular camera?
Yes.
How you process them?
I just took
what software or
What
what algorithm did you use?
I think, did you use the regular camera, correct?
Yes.
Okay. And the image processing, what kind of the techniques did you use?
I can return to the pipeline.
Yeah.
So, are you referring to this
Yes.
steps?
The second box.
This
Before the bounding box.
this.
The second.
This one.
Okay. So to pass from this to this, we implement a faster RCNN.
All right.
So it's a single step model for object detection.
Ivan.
Just to mention, not to steal too much time, and Julia's answer is correct, of course. What we did here is kind of a play with many different pipelines, and we try them. It's a craft work. You know, how to prepare the materials, the images, and the bounding boxes so that the multimodal AI can make less mistakes, hallucinate less.
Yeah.
And by playing with tens of variations, we settled with this one. Of course, we can never be sure that it is the most efficient one, but it was sufficiently good enough to give us and in the paper you will find all the little individual libraries that we use, because it is the second bounding box which is actually it is a more interesting one. This is how you hint the AI that there are social configuration, and this is where it makes a lot of mistakes. And Julia has mentioned now what we are experimenting right now is trying to do this, implement this pipeline adapted on videos, where we suspect the AI will make less mistakes into understanding whether people have movement, because just picture sometimes even us are not able to say if someone is walking or it is just a still that was taken. So videos could be, I think, interesting advancement to be able to be more precise in identifying what kind of activities people are making.
Okay, thank you. There was a question there, and then it's you.
I was wondering, is it important for neural network that the images are in the same resolution? Because camera is different.
We use the same camera for all the pictures, so with the same resolution, but we can test with other resolution. I don't know.
Just a quick comment and suggestion. I don't know if you had the chance to look at a long time work made by Veloso, which is from who is a professor from Carnegie Mellon, who made a lot of experiments on taking out the attitude of people from videos. And particularly one of these approaches has been used a lot in transportation. For example, in recognizing, in enhancing the security of particularly risky places like galleries, something like that. And it would be Cameo. I remember the acronym CAMEO. Would be a cue to.
Thank you.
Thank you for that comment. Before we have to move on, is there any last question that you have? No. All right. I gather that it was Julia's first presentation today, and I think we all can congratulate her on a very successful. Thank you, Julia. Now it's for the final talk. We have it in a virtual way. So I call on Rodrigo Tapia McClung, Rodrigo Lopez Farias, and Camilo Carrillo. Sorry if I misspelled any name.
That's great.
I'm afraid we have to keep to the time because the closing session will start at 12:20. Okay. Rodrigo, the floor is yours. Thank you for attending.
Thank you. Let's see here. Oh. Hold on, I'm just getting a there we go.
We can see you, we can hear you.
Share your screen. Yeah.
Oh,
okay, perfect. No. Just leave. Maybe misclicking here. He misclicking and then leave. Okay.
There we go. Let's see if I can check. Can you see my screen now?
Yes.
That's good.
Let's go in full mode, please.
Presentation mode.
Okay, perfect.
Yes,
Thank you.
Great.
Here you go.
Oh, thank you very much for everyone being here. I don't know how many people are in the room, and but I'm just glad I'm here and being able to present this time around. I wasn't able to go there, but today's topic is about trajectory analysis applied to crime incidents. It's a collaboration between myself, Rodrigo Lopez, and Camilo Caudillo. And as a very quick introduction to this topic is that our goal is to understand and communicate crime incidence trends, in particular in Mexico City. So our approach is to apply different count-based trajectory analysis, and I will explain a little bit further what we mean by count-based trajectory analysis. And for our case study, we're going to focus on larceny theft in Mexico City, so pedestrian theft for the past 5 years. And what we're going to end up with as an end result is try to follow in different spatial units if there are gains or losses within each cell or hexagon, as we'll see we are working with, or if there are alternations. I mean, if one cell gains larceny depths or is losing them throughout time. The idea behind this, and in order to do this, is that we can follow through time and space how things are happening in a certain like policing unit. Longitudinal studies and trajectory analysis are typically used in life course studies and land use change, and we're trying to see if this is possible to adapt as a methodology to crime studies. We haven't seen many applications of this methodology to crime data spatially, and what we have seen in the past is that specifically for land use change, trajectory analysis has been used, but only for binary cases, whether a certain class exists or not in the data. So we're trying to adapt this to count-based, to incidence-based. So trajectory analysis is useful in classifying locations that change over time and that have either presence or absence. So they exist or they don't exist. In the figure at the bottom, we can see a schematic diagram of how this works. So we have different trajectories T1 to T4 from top to bottom, and then we have different maps in which we can see either black dots correspond to the presence of this category, and the white space or blank space represents the absence of the category in a particular map, in a particular trajectory. So at the beginning, we have very few types, meaning that one of the trajectories can be shown or is presence, then we can have a loss of that presence, and so we have absence, and then maybe we can gain it again, so it's present, and then we can lose it again. So there's shifts. It can go up and go down, and essentially we can classify that trajectory through time and space in different types. So this particular one, this T1, we see it's essentially we compare what happened at the beginning and what happens at the end, and because we started with presence of this certain category in this map, and we end with the absence, we classify that as a loss, but in between there are changes. So we say there's an alternation, but the general trend was there was a loss and there was an alternation. Similarly, we can consider another trajectory, which is called gain without alternation. So we didn't have any presence of that category through in the first three maps, and at the very end we have presence. So there was a gain. Overall, there was a gain, and there was no alternation because there were no ups and downs, or presence or absences. And the last one, it was always alternating, and at first there was nothing, there was absence, then there was presence, and then there was absence again. So we were always alternating values, but at first we gained. And in the last case, we also have a gain first, but it was not in the very first map. So we then turn this type of trajectory, we turn it into a trajectory plot, which allows us to visually see if those trajectories, how can we map those trajectories in terms of gains and losses, and how those gains and losses contribute to the overall change in time and space. So this is a useful way to summarize all these changes in different pixels or different cells through time in terms of the whole area study. So we can change these contributions of different particular pixels through space and time. We can plot them in this bar chart or stacked bar chart that represents gains and losses or alternations as percentages of the area study. And we can also represent the average gain and the average loss throughout time through different time periods. For For our particular study, we focus on Mexico City, which is roughly 1,500 square kilometers and has about 9 million inhabitants. We use 5 years of larceny data from 2019 to 2023, which correspond to roughly 55,000 crime events. And we use this H3 level 7 grid, which is a spatially like a special tessellation of space that is continuous, and it's very used in the literature. We cover the study area with 301 hexagons, and we decided to use the spatial tessellation in order to reduce spatial bias in terms of the sizes of policing units that exist in the city, which we can see in this map in the left here. We can see that the areas are very different from one to another, so we decided to use this H3 tessellation to sort of focus on getting rid of that spatial bias due to size. If we take a look at the distribution of crime events throughout the years, we can see that 2019 has the highest count for one particular cell, which is roughly about 750 larceny thefts in that year. And as time progresses, we gradually see a decrease in incidents per cell. This agrees with official figures and reports that state that larceny theft has been increasingly or decreasing every year since 2019. So we kind of confirm that general decreasing trend throughout time and space. When we summarize our trajectories with the trajectory plot that I just showed before, then we have different kinds of interesting things happening here. We can see that we can't confirm that from 2019 and 20, from that period to the next, we have a very large decrease in our presence, which can be seen from the size of this bar to the next. So that sort of relates to the size of these values here in the maps to the next years, which have lower counts. And what is also interesting is that we have a lot of loss with alternation values in here, which are the pink or light reddish bars. So overall, we can confirm a general drop in larceny. And the next one, when we see the spatial distribution of trajectories, we can see that there are, it's a very interesting trend here that we do not see overall in this bar chart, but when we plot them in space, then we can see very interesting things happening. So all this part here at the bottom is mainly conservation areas. There are very few urban settlements in there, just a few over here we can see in these cells. On the largest chunk of the urban concentration area, which is the central part or the northern part, have we can see they have a loss with alternation trajectories in most of them. Some of them do have losses without alternation, but we can see that the overall trend in the central part of the city has a decreasing pattern. So it goes that helps us confirm again what the official figures say, that they're going. We have decreasing numbers of crime incidents. So there's no surprise that in this portion here we don't have urban settlements, that we don't have reports. So that's why those are classified as a stable absence, because we don't really have any reports over here through time. And this last plot here shows us that there is a different kind of behavior throughout the years for particular cells that are classified as a certain type of trajectory. Because here in this map or in this bar chart, we don't really see what's going on for different trajectories. We only see the overall pattern of all of them. And in this one here, we can only see how cells or hexagons were classified for the whole period of time, but we don't really know what is going on from one year to the other. So in this last plot here, we can see that for different trajectories and different cells, we have some ups and downs, and things are certainly changing from one year to the other, so we can capture a little bit more of the behavior throughout time. What we're working on is trying to get these two things together so we could plot trajectories for both space and time, but in one map, to gain a better idea of how things are changing from one year to the next in a particular cell that is either classified as a loss with alternation or a gain with alternation or any other type of trajectory. What we do have, what we can see here also is confirmed that there is a general decrease in pattern of incidence count in cells for many of the trajectories that we see. Some of them have a slight increase, but it's like from 5 incidents to 15, as opposed to decreasing from 300 to 100 or 600 to 200 or things like that. So we do believe that the visual trajectory plots help us reveal certain crime trends or patterns. Those are complementary to standard incident maps that we've seen before, and we believe that this analysis could support resource allocation decisions to see where certain programs or actions could be implemented in space. Now, this study, because we use this data aggregated yearly, there is no reason why we couldn't use it for different time resolutions, like weeks or months, to focus on more particular actions that have been taken and see if they are actually working or not. Another important thing that we want to do is, or that actually we're working on, is the sensitivity analysis, how the cell size impacts the results of these trajectories. So we are shifting our study from cells, hexagon cells, to square grids of different sizes to see how that impacts our results. And also, as a result of this, when we're working on cell size, when we use very small cells, our maps show like spatial noise. So we're trying to see if it's possible to determine when there is a specific or an optimal scale of the analysis, or if we can filter all that noise, spatial noise that we see on our results. And this ties in with this last bullet here, that we're working with test square grids as opposed to hexagons. As our conclusions, we do see that count-based trajectory analysis reveals spatial temporal crime patterns, as we saw from the cells, and which is potentially useful to evaluate crime policies and interventions that have been happening in different moments in time. And even though we see there is a general decrease in larceny, there are some spatial nuances that are important to address and that we are currently working on. And with that, it's the end of my presentation, and I thank you very much.
Thank you, Rodrigo, and also thank you for being very strict with time. So this gives us time for one or two questions. Are there any? Okay. So there's no questions, and take it as a compliment, because you made a well-structured case. Yes, it is. It was well organized. It was well presented, and everyone got the message that you wanted to bring across. So thank you for that, Rodrigo.
Thank you.
it's good that at last, you know, the virtual version worked. Hope to see you some of the next conferences in present. And with this, I think we've come to an. You have a question, Deborah? With this presentation, we are winding up this session. So thank you to every presenter, to every participant. And before I close, I would like to encourage you to consider to submit a paper for next year's conference and the GeoMod sessions. We've heard last night that next year's conference will be in Portugal. So this will be an attractive destination, I guess. So please do consider to submit papers so that also next year we have GeoMod sessions. So we have now some time. We're very much in time for the closing ceremony. Thank you everyone for attending. And a special thanks again to Simona for doing the technical things. Thank you very much. I will see you at the excursion. And thank you.
Thank you.